Okay, great. Thank you for being here. I'm William Robinet from Luxembourg. Today I'll talk about a very small vulnerability I found in some cryptographic toolkits. So this is for sure important to worry about post-quantum world, but sometimes the vulnerability lies elsewhere. A few words about me. So I am the CTO, tech lead, responsible for acoustics in Luxembourg. This is a small company. We're doing cybersecurity operations, data centers operations, cyber services. I'm also a part of the new B-Sides Luxembourg organization team, for which I invite you to submit your talk and workshop proposals for next year. It will be around 6th to 8th of May. I appear to be a CubesOS user. You have my contact information on this slide. On the bottom of the slide, you can see that there is a Codeberg repository link. That's where I will put all the content of this presentation. So right now it's empty, but I will do it later on. You also have some subliminal information about some of my activities on this slide. Right, so the outline. First, we'll skim over the boring stuff. So I'll talk about the standards that we'll consider here, being X509, ASN1, the RPM. We'll see what are all these. We'll talk about the vulnerability that was released in 2022. That helped me release a tool I wrote earlier. I'll tell you about the story behind this present talk. I'll show you what I experimented and what were the results, and whether there is some real-world implications. All right, so let's dive into the boring stuff. So X509 certificates, you probably all know them. Those are used for instance, for SSL TLS. These are actually some encoded value that were at some point in time specified by an ASN1 message specification. So ASN1 is basically a structure you define with an abstract language that you can later on find as a concrete structure in a file, being binary or whatever. So here is the pretty print of X509 certificate done by the OpenSSL command OpenSSL X509. This is the google.com certificate that was online earlier this year. So where you can see different fields such as the version of the certificate, the serial number, the validity period of the certificate, the command name, so the subject of the certificate, the issuer. But you probably already know all this. What is ASN1? Basically, ASN1 is a language that you can use to specify interface. Let's say a message that will be used for interface. You can see this as the specification of probably an API. So what you do is you define some messages in a kind of abstract way, and you can later on encode them to concrete messages that you will use with your applications or devices or whatever. So it was written and invented, defined or specified during the LDAP days with the X500 standards, but it's still actively used for current standards such as LTE, 5G, 4G, and so on. And each day we are using it basically because we are surfing the internet and we are using SSL and TLS certificates. I encourage you, if you're interested, to look at the link I have at the bottom of this page here. Let's Encrypt did a fantastic job in explaining this stuff. And honestly, most of the first section of this talk is based on this. So here is a grossly simplified X509 certificate written in ASN1. So what you have is the top-level structure is a certificate containing three stuff. The to-be-signed certificate, which is later on defined as being a more complex structure. You have the name or the identifier of the signature algorithm, and you have the actual signature. The to-be-signed certificate is, as you can see, a sequence of different fields, being the version, serial number, signature algorithm identifier, issuer names, the validity period, and so on. So This is just a simplification so that you get an idea. If you want all the gory details, you can go and check the RFC for that. In ASN1, you have two different, let's say, kind of types. First one being the basic types, second one being the structured types. Basic types are the one that actually contains the actual information, such as Boolean, integers, text field, ID number. Structured types are more just used to build structures, so that basically this is just, for instance, the sequence that you really see most of the time. Sequence, in sequence, in sequence, in sequence, that finally built trees. Trees such as what we saw earlier, for instance, a certificate. Because a certificate is actually a structure that, when you view it, is actually a tree. With ASN1, you have some, let's say, predefined types. But you also can define your own types. This is done by using classes, tag classes. So by default, the classes is universal. So the ID number 2 specifies that the field is an integer. But you can change that if you use other classes, just application classes, context-specific classes, or private classes, and you can say, okay, now the number 2 is not an integer anymore. This is application ID number 2, which means that I decode this as something else, for instance. And you can have implicit or explicit tagging. I won't go into deep details with this. It's not really useful, this presentation. I just talk about this so that you have, let's say, a gross idea of what we are talking about. Once you have your ASN1 message, which is just an abstract specification, you will have to encode it to actually use it within your applications. In this talk, we're just considering BER and DER, which are the two types of encodings that are used with classical cryptography stuff that we use daily, such as OpenSSL. But there are many more, and most of them I've never seen them. If you appear to see them, I would be curious to see how it looks. Some of them are binary, some of them are text, I guess. Especially maybe the XML or the JSON one, I don't know. So what we have is ASN1 on the left and DER, which is the encoding of the message, on the right. This is the case, and it's for the certificate. So what is this encoding? So we have BER, DER. This is basically binary encoding for ASN1, which is built around the TLV principle. So when you have something that needs to be encoded, you will first encode the type of the data you want to encode, the length of the data, and the actual value of the data. So if you have a byte that takes maybe, an integer that would take 2 bytes to encode, you will have 2 because 2 is the type of the integer, length is 2 also, and value might be whatever you want that you can encode in 2 bytes. There is a difference between BER and DER. As far as I can tell, BER can encode ASN1 messages in 2 different encodings, where DER is more like a canonicalization of the BER messages. That's also why you will not find sequences with undefined structural lengths in DER. So how do we encode everything? So you have the tag value, 2 for integers, for instance. You might have a class that is not universal, so you might need to tweak a bit your encoding. For encoding the class, you will need to use bit 7 and 6. Bit 5 will tell you that the object that the tag that you are encoding is primitive or structured, so being basic type or a sequence or a set. And you also have the possibility to do that explicitly. That means that you simply embed everything in a tagged sequence. Not really useful at this point, just so that you are informed about that. So here is an example of encoding. I have a basic structure, which is a sequence with 2 integers. First one being value 12 in hexadecimal, second one being 34. As you can see on the left, 30 is the type a number of the sequence, you have a length of 6 bytes, and then you have both integer, being 2 for the identifier of the integer type, 1 being the length, and 12 being the value for this one, and so on for the next one. Finally, you end up with a completely encoded ASN1 structure. In this case, again, the certificate from google.com that you can print like this with the command you see on top. So basically, this is just binary stuff. You can, if you look on the right, see that some fields are actually encoded just like you wrote them in the ASN1 specifications. Here, what you see is that I download google.com certificate, I convert it to DER, and I decode it from DER. So this is just almost the same command as this one, except that instead of piping everything in the XDOM to see the content of the binary stuff, I simply decode it to have a pretty print of the certificate. And compared to the first pretty print of the certificate I showed you, here I just go through the DER conversion. Right. When you have a DER structure, this is binary, it's very hard to read by a human. So with OpenSSL, there is this ASN1 parse command that you can use that simply takes as input a DER file, so again, the google.com certificate, and simply parse it. Here I just tell ASN1 parse that the format is DER, this is the D here, and I want with -I to indent the content so that it's more easily readable. And here you can already see that the structure is actually a tree, with the topmost element being a sequence. Right. Then comes into play the PEM format. So PEM format is simply used because transporting binary data over text channels such as email is quite not always functioning as expected. So what we can use is PEM, so that we simply encode the DER binary format into base64 format, which is pure text, ASCII text, without any fancy UTF stuff. And so you can copy-paste basically the content and simply keep it as a text file. Really useful. Right. PEM format specifies that you have in the, if you look at on the top here, you see that this is a begin certificate. That means that what's in there is a certificate. In the OpenSSL world, you have many, many different type of objects that you will transport using PEM. We will just consider a few here, being X509 certificate and certificate request for the next part of the talk. Right, enough with the boring stuff. Let's go with the rest. 2022 was published vulnerability in OpenSSL. Actually, vulnerability was that with some format of certificate, namely elliptic curve certificate, you could edit the content, or you could use some specific numbers and send your certificate to something that manage it using OpenSSL, and you would end up in an endless loop. That's simply a DOS, so your server wouldn't answer anymore. A few times later, the first POC appeared, and what they did simply was to use an existing certificate and change manually the content of the certificate with all the values that would trigger the vulnerability. It's still published these days. So on the left you have what you need to change, on the right you have what to change. As you can see, this is a pain to do by hand, because once you change something into the inner structure of the tree, you will have to adjust all the lengths field of all the surrounding sequences. So when you have simple structure, it's kind of easy, but when you have something like a certificate that is kind of, let's say, complex, you will spend a lot of time doing stupid stuff, because this is not really interesting to do. So I came with an old tool that I wrote long times ago, many years ago, which leverage another option of ASN1 parse, which is the possibility to generate a structure by using a given, let's call that configurations. That's how they call it in OpenSSL world. I called it a template on my side. So ASN1 template that is available on GitHub is a Perl tool that will simply read a DER file using ASN1 parse from OpenSSL, which is actually just a visualization of the content of the DER file, just not a pretty print. I simply take all this, I recreate a complete tree, I traverse the tree, I recreate something that is compatible with the configuration format of OpenSSL, and I call that a template. It was written in 2010, before their ASCII was born, so, and it's all in Perl. It only depends on the OpenSSL SSL CLI. So here it works. So you take test DER, which is just a sequence with a few sequences in there, a few integer. You converted it to what I call the template, which is in the format of configuration of OpenSSL. You can go back with genconf, the option genconf here. You take the template and you get back the structure you started with. And if you do a diff between the first file we had beginning, so test.der and test_reconstructed.der, we can see that there is no difference. It means that I can take a binary encoded DER file, go to a text equivalent, I can modify, or I can simply reuse to recreate the original file with just a text editor and no hexadecimal value fiddling and so on. Here is an example of an edition of such a template. So in this case, what I do is I replace, if you look, the last integer here is replaced by a printable string. So you can see both structure compared here. And it's just a matter of one command, one simple replacement here, where I change integer OX1234 with printable string hello. Really simple. And with the power of the simple configuration facility of OpenSSL, I can recreate the whole structure as complex as it is without having to even understand the binary values and adjust anything. So the story behind this talk. Last year, I was here at Akelu, and Alex asked me, do you want to present a lightning talk? There are still some slots available. And I said to myself, okay, maybe, there is a bug in ASN1 template, actually. It doesn't support the fact that sometimes you have line return or line breaks into the output of ASN1 parse. And that gave me an idea. Maybe if sometimes certificates are from the wild, so sometimes you have some crazy stuff in there, as you will see later on. So it appears that sometimes some control character gets evaluated. So that's interesting. And I started to work on that here at Akelu last year. But actually I didn't manage to have something as I wanted. Here is an example of the problem that you can see with ASN1 parse, which is something that I saw while testing my tool with a corpus of 1.7 million certificates I found on GitHub at that time. So you see that there is an octet string that is split in two lines. Okay, so that means that there is a line return here that is interpreted in the output of the ASN1 parse command. Right. Actually, this was already reported back then, because probably some of you may know that when you try to print the SMIME field of a certificate, you will see that there are plenty of line breaks. So that was already a hint that something was probably usable in that. Experiment and findings. So I stole this squirrel graphics from the tool called Polysay that you can simply use to have such a tiny animal saying something on the screen, because I needed some NCR to try this. And what I wanted is to validate the fact that I could make the OpenSSL tool print raw character escape sequence so that I could exploit something on the terminal with that. Two approaches were tested with this. First one was to use a certificate assigning a request, and the other one was simply creating a structure with some kind of placeholder in there that I could simply exchange with the content I wanted to print. Right. So a few words about control characters. So basically you have three types. at least on Linux, Unix. Probably something similar exists on Windows. I don't really know. All this was tested and is still testable on Linux. So you have the control characters that are mainly there to control movement of cursor, maybe interpret backspace, maybe add some space, stuff like this. And you have control sequence introducer that can be used to change the color, for instance, of the text. And you have also operating system commands that mostly nowadays are completely disabled, but that could be used to start applications. This was already weaponized many times by different people. There is this presentation talk recording on YouTube. You can go and watch, and you will have all idea of what was possible at some point. But we are not doing that. We're just trying to print something raw as raw as possible. So here, for the ASCII control character, you see that, for instance, you have backspace, horizontal tab, which is \T, you have new line, vertical tab, interesting this one, form feed, carriage return, escape, space, basically movement. Terminal escape sequence, so those ones can be used to change the color of the text. Here I simply start with this comment here to say that I want it to change to red, and then go back to black. Right. First finding. It appeared that at some point in time, with OpenSSL, they decided that it was a good idea to activate UTF-8 in CNAMEs by default. I said by default because this is still possible right now, but yeah, we will see that. I don't know why, but as a side effect, control characters were also allowed at this point. I'm not sure it was necessary, but it appears that they are available. This has been fixed because I already presented this result at NullCon Goa in March, and just before the conference, I had the confirmation that it was fixed. But it was never considered as being a security vulnerability, so there is no CVE, nothing for this. So here is the first demo. So I am here on OpenSSL 3.4.1, and I try to print my NCR certificate. So here we go. So as you can see, I managed to do something. And there is something interesting in this picture, being that, after the CN in a certificate, you have plenty of other information. But there you can't see it. But it's still there, because the certificate is completely valid at this point. Now, if you want to, let's say, validate that your certificate has been exploited with such things, you can pipe it to less. You will see that actually the subject contains all the graphics, and then after that you have all the rest of the certificate. But for some reason during my test I noticed that, it was not, it was simply stopped. Nice. Pretty useful actually. If you pipe it into less, for instance, if you use another version of OpenSSL, for instance, let me switch to maybe another one, or maybe a new one. For instance, this one was released, I think, 1st of October this year. So if I try it, you see that it's not working anymore. But I still can do something like this, and it works again. So what we see here is that when the tool is meant to interpret or instructed to interpret UTF-8, it also interprets control characters. Okay. Not sure this is necessary, but okay, this is it. Right. Okay, so this is the same. Yeah. So when I tried this with text, I saw that the rest of the certificate was still printed. So what I tried is I tried to show a given certificate, which was not the actual certificate you were looking at. So basically what I had is 2 blocks of signature. That's what we have here. And then I analyzed what was happening with the graphics. And I found this. Let me show you with the example you will see. Here is I have a simple file containing blah blah with 2 line returns. I have the same with bli. Okay, so if I do cat blah blah, I have this. Right. Now, if I put this in the middle, oh. And if I do this, oh. What the hell? So, this is working with, you can put that in the xdump so that you have all the file. This is working with, in my case, GNOME terminal. I tested many different terminals. Sometimes it works, sometimes the terminals go crazy. It all depends. What is this? It's actually an unterminated operating system command. So you simply start, you tell the system, okay, I want to do something with the OS, but you don't simply, you put a line return and you don't give the command. And then, for some reason, the rest is not printed. So that's nice. So now I can inject text and close the output. What are the real-world implications for that? The thing is, if I can inject some text content into a certificate request, for instance, I could trick an administrator to sign something he doesn't want to sign. So, this is what we will do. Where's the demo for that? Here is, this one works with the CN. So this is a CSR, as you can see. Completely standard certificate request. This one is for blah.lu. Excellent. So I'm using, I'm a hardcore operating system geek. I'm the best administrator in the world. So I'm using the CLI. Okay, right. So my user is asking me to sign blah.lu. Fine. I will sign it because, okay, I have to. Maybe I'm using EasyRSA because EasyRSA is a better way to manage a PKI, but you have to know that EasyRSA is basically just a wrapper around OpenSSL. So when you try to show a certificate request behind the hood, it's using the same command as this one. Right, so I sign it. But if you pipe this in less, you will see that actually what I signed was a wildcard for google.com. Yeah. So that means that someone has a certificate that is certified by my internal PKI of CA, and that can impersonate start.google.com. So obviously this will not work with Let's Encrypt and so on, I hope. But yeah. As you can see, we add some version of OpenSSL at some point in time that would simply print it beautifully. This version here is the one that was vulnerable because I'm using the CN field for that. So if I'm trying this with a newer version of OpenSSL, which is the last one that was released, okay, it doesn't work, right? Unless I use nameopt UTF-8 like this. Oh, it works again. Okay, but this is not vulnerability apparently. Right. Findings number 3, and this one is interesting because all this also works with the subject alternative name fields. This is not fixed, and this works since dawn of time. Namely, in my case, I tested it with OpenSSL 097M. This works. So with this one, you can actually inject text in the send field of a certificate. So here it is. I am on the last version of OpenSSL here, and I can inject stuff in there. What have I done with this one? Yeah. This one is a bit different because what I'm doing is that I'm clearing the screen and then printing something. So you have the original certificate here that is simply removed from view, and I replace it with another one, which is this one. It was just a test, but it works. So this is encoded in the send field of the certificate. If I put it in less, you should see it. So we have the certificate, which is the actual one. And then in the send field, we have a DNS, in the send fields, we have a DNS record that is a complete mess of stuff. Excellent. Right. So, and this works with many versions of OpenSSL. If I switch to 0.9.7, I hope you don't have this one anymore in production. It's one for 2007. This should work too. So you can see that my clear screen was interpreted at this point. So that means that any kind of stuff I put in there would be interpreted. Right. So, were these techniques ever used? I asked Circle if they had some data sets of certificates. I received something like 112 million certificates and many more. But yeah, unfortunately, I saw nothing in there. But I saw stuff. The smallest certificate that is valid is 225 bytes. This is nothing. The largest one I found is almost 60 kilobytes. Yeah. You have to know that with TLS SSL, the maximum is 65 kilobytes, or 64 actually. So, well, right. And what did I find in there? So I built a few tools to try to identify, let's say, uncommon structure. And I found some oddities. I didn't find something that could be called an exploit for what I showed earlier, but okay, we have some strange stuff. So, variable expansion failure. Yeah, okay. It looks like something, let's say, familiar. You have custom structures, such as those ones. Maybe this is something you know, I don't know. You have things like this. This one, I don't know, but actually, this is a backspace. So what you see here is that when this person created the certificate, he started to write hotmail like this, OTM, then went back 3 characters and restarted writing hotmail. Right, and you have plenty of those. So there is somewhere an implementation of the cryptographic stuff that we are using that is encoding the backspace actually. You have those kind of things. So you have private keys in some fields of certificates. You have those kind of crazy stuff with, this is actually a line return. So when you print it, you can't see all the contents. You have to pipe it in some hexadecimal editor or less maybe to find stuff like this. So in conclusion, I would recommend not to trust, or let's say to be careful with the output of your own tools, or pipe the output into less. So now, bonus demo. Yeah, I say, okay, I cannot end like this. So I try to, let's say, encode a video in a certificate, and I somehow managed to do it. The point is that it's difficult because there is no control character to induce some pause into the terminal. So I needed to use some trick to do something like this. Let's do it again. So this is basically a completely valid certificate that is waiting something like, you see it, 23 megabytes, 31 if you encode it in PEM. And what I do, this is just 16 frames. So what I do is I do pausing between the frames simply by writing stuff, erasing stuff a lot of time. And that constitutes most of the content of these files. So those files will be available on the repository down there. And that's it for me. Thank you for the attention.